welcome to the last section of college prep. I'm sorry, last section of college prep, but last section of the Unit 10 notes. It's common logs and natural logs. I do apologize, it says section 7.4. We are not in 7.4, we're in 10.4. I adapted this notes and I forgot to change that one. It is current on yours. So we are in the common logs and natural logs section. So far we have talked about inverses and how they relate to logs. I'm going to just head back up there for a sec. Ooh, hold on. Okay, so we talked about inverses and their function, inverses as functions, inverses of functions, and how those two relate. We've talked about exponentials and logarithms, and those, how they're special inverses, right? How we needed a new one, this logarithmic thing. We've talked about in 10.3, most recently, the rules of logarithms and how you can simplify them, and then we also talked about transformations of logarithms. The last thing we're going to be talking about is something called a common log and a natural log. These are two that were coined to be the quote-unquote, in people's opinions, most important logs. And I know I say that very asterisk, right? I say that with a very large asterisk on it. These are not the most important, they're just the ones that occur most often, okay? So if we look quickly in the vocab, the common log is a base of 10, and the natural log is a base of e, okay? So basically these two, we're going to talk about what that means in a sec, but basically these two have special bases. They're so basic, it often is just, it's overlooked, okay? So let's start with common log. Common log is base 10, right? Here's an example of a common log. Notice how there is no subscript. Up until now, we've always had a subscript. For some reason, mathematicians hate writing 10. They never do, right? Calculators don't say times 10 to the, they say e, right? You don't write to the first power, stuff like that. So in this case, log 10 just got too much for somebody to write. It was just too often happening. They didn't want to deal with it. So common log is just a log base 10. Okay. So if we have the log here, we can see it not as log 10, but as what we have been seeing out, log 10 100, and what they're solving for is equal to x, right? So this is kind of the shorthand version on the left of something we've been doing before. We've done this before. We did it in the couple sections ago. We did that in the last section. And then they made the circle, right? You get 10 to the x is equal to 100, therefore x is equal to 2, right? So log 100 is equal to 2. Cool. That's pretty much it. That's nice for powers of 10. Right, you got 10, 100, 1,000, 10,000, a million, stuff like that. But what about log 2, log 12, right? And then essentially what are you asking? You're asking about to what power of x is 10 equal, to what power of 10 is 2? That's hard. So, lucky for us, this entire section is about calculators. That's why you see sort of a different format here. You see both the movie that we usually have and this over here, you see my calculator. On your calculator, you're going to find your log button. Chances are it's not going to look like mine. Please don't use your phone. Just don't use your phone. Unfortunately for the on-screen calculator, I do have to use the Apple calculator. It's not great. It doesn't log fast enough. It just, there's play on words. It doesn't, it's not that it doesn't calculate. It's a perfectly fine calculator, but when it comes to the software behind it, it doesn't read fingerprints as fast as it should, as a button calculator would. So you often trip up, you hit the wrong key, you hit the key twice. It's just so complicated. I'd rather you just get up, go use one of mine. I give you free calculators. Okay, so having a calculator, not being able to use a calculator is probably the dumbest thing you can ever say about yourself. Please don't be that guy who can't use a calculator. I don't know how to say it nicer because it's so maddening to me. Please know how to use a calculator. It's just dumb. Okay. Again, on yours, it's going to look a little different. I'm not going to take the time to go through every single model of calculator and show you where the log button is. But it's going to look something like this. In fact, it's going to be looking even simpler than that. It's just going to say log, L-O-G. So go ahead, take a moment, find your log button, L-O-G. It might be in the subset of buttons in the upper, on a TI-38, it's purple. right? It's in the purple. Most calculators have a log button. If yours doesn't, get a better calculator. Okay, so you've got log here. For some reason it says log 10. That's unnecessary because we know it's log 10. Common log is log 10 no matter what. So what we're going to do is we're actually going to use the calculator to solve these. But why do we need the calculator to solve this? Why would we need that? Well, let's convert this, right? We know since it only says, I'm down in example 1. Use the calculator to approximate the common logs below. So I'm looking at A here. I know it's a base of 10 because it doesn't have a subscript, right? Kind of like when I see 2, I know it's 2 to the first power, even though it doesn't have the 1 written there. I know that it's there. When I have 6, I know it's 6 plus 0, even though it's not written there. It's left off. Okay, so I know this is technically log 10 to the 327.1 equals x. So the question is, to what power of 10 is 327.1? Do that in your head. I dare you. Please don't do that in your head. That's a waste of time. So why don't we just plug this into the calculator? Here's what we're going to do. We're going to hit log, not a number. Okay, so we're not going to do it that way. We're going to hit 327.1 and then hit log. Sometimes it has you go backwards. For other calculators, it may have you on the TI 38s. It actually has you enter it within the parentheses. You hit log first, and then you close the parentheses. Those are the instructions that are written up here, okay? But in either case, it looks like this is equal to 2.514. We're going to round it off to 2.15. And my son is not happy about my choice of rounding. Just kidding. Okay, and that's it. That's literally it, the common log. But just knowing what it means, what you found, it means that 10 to the 2.515 power is going to be, that doesn't sound right. Did I enter that right? 27.1 log. Alright, let's try it. 10 to the 2.515. Hey, look at that, it is. Even I was concerned for a moment. Sorry about that, need to trust myself more. So, that's what I just found. To what power would that be? Well, 2 to the second, you'd think, well, that's just 100. But then you've got 2 to the third, that's already 1,000. So somewhere in between there is going to be the answer. 2.5 sounds about right. If you don't like it, check it out, right? Double check your work. Always a good idea. All right, let's go over to B. Log of 437,000. Once again, that means 10 to what power is 437,000. That would be so nice if it was 100,000 or a million, right? Because then I'd have a nice whole number. So it's somewhere in between 100,000 and a million. Let's see. Well, 100,000, that's 5 zeros, so that'd be 10 to the 5th. A million, that's 6 zeros, so that'd be 10 to the 6th. So it's somewhere between 5 and 6. Let's try that out. So 437, 1, 2, 3, log. Oh, hey, look, I was right. 5.6. Okay, cool. So that's equal to 5.640. We'll go 3 decimal places each time. 5.640. Cool. We found it. So it's not super complicated. Okay, it's not super hard. Let's keep going. Log of 0.0615. So this is going to be a negative number. How do I know that? Because I'm looking for what power of 10 goes down to 0.615. Well, if it goes down, that means it's cutting this 10 in half. So it's going to be a negative number. But let's see exactly what negative number. So 0.615. Boop. Ah, negative 1.211. So this equals negative 1.211. And the next number is a 1, so I don't round up. Easy peasy. Last but not least, log of negative 5. Okay, so log of negative 5, let's plug that in. I've got 5, which is negative. This is why I also don't like the online calculator, because you have to do negative second. And log. Interesting. Not a number. Why would that not be a number? That doesn't make any sense to me. Why would that not be a number? Let's take a look at that. 10 to the x power, my apologies. Happened again. It's been happening all the time. But that's okay. It doesn't rattle us. All right. 10 to the x power equals negative 5. That's why. That's why. Because to what power of 10 are you going to get a negative? No power of 10 is ever going to turn negative, right? If you go in, if x is positive, you get bigger, bigger, bigger numbers. If x is negative, you get smaller and smaller fractions. Remember what a graph of a log looks like, right? It looks like this. Whoosh. Are we ever going to go into the negative side? No, we're not going to go into that side. So this makes sense. This does not exist. We can write DNE does not exist, no solution, whatever you want to write. Right, not a number, like it says up here, whatever you want to write. But it doesn't exist, and that makes sense. Okay. Excuse me. All right. So that's log base, or that's common log. It's not super hard. Plug it in your calculator, right? It's to the power of 10. The other one we're going to talk about is natural log. Natural log has, and also a common base. But this base is for the letter E. This letter E is a universal constant. It's a fundamental number. It's something that occurs naturally in nature. Why, we don't know. But it's also, so it's very much like pi. It's also an irrational number. If you see down here, it's about 2.7718, and it goes on and on and on. Even the number I've printed here is an approximation. But it's another one of those irrational numbers. You might be thinking, why the heck did they choose E? They chose it for this guy over here. His name is Euler. It's pronounced Euler, not Euler, as though I often find myself saying. He is the one who discovered it, so he got naming rights. So he called it E and made himself immortal, which is cool. He actually did a whole bunch of other things. If you'd done him for your project, props to you. It's pretty cool. But yeah, that's why it's called E. Fun fact. But it occurs everywhere. Everywhere. One of the biggest example is in the growth charts of little kids. Right, so hopefully none of you have ever had a child. If you have, more props to you that you're still in school. But if you've had a child, you have seen one of these charts. Or if maybe you remember way back when at the pediatrician, or if you just think about it for 30 seconds, right? Kids grow super fast in the first 5 years, and then after that they taper off, right? So this is birth to 3 years, 36 months for girls, where you can see length of their height, right, length, because you measure a baby laying down, and then their weight, right? So we can see it gets super, super dramatic and then tapers off, right? And that's a logarithm. It's a logarithmic function. Like, check that out. Whoosh, just goes straight up, woo, all the way. And it kind of tapers off as it goes up. Well, that logarithmic function is so common, the way that happens. Most things grow in this way. They grow in this logarithmic function. So naturally, it's called the natural log. This is a natural log with the base of this 2.71 number. It's actually pretty exciting. Also kind of hard to find answers to this kind of log because 2.718, or 2.71828881828 is an incredibly hard base, right? So we don't want to solve this by hand. So we can solve it in our calculator as well. This is the natural log, like I said. For some reason, I believe it's like in French or something. Euler sounds French to me. I'm not sure exactly what language, but it's called ln because it's kind of like Spanish, where log de natural or something like that, where it's flipped around. Okay, so it wasn't coined in our language, so it doesn't make sense to write NL for us, or it doesn't make sense to write ln for us, but it did in the other language. So it's ln, natural log natural, whatever you want to say, and it's the base of E. This is equal to a log base of E. I'm sorry, ln of x. We do still write the argument, ln of x. And that's just log base of E. Rather than writing log E to the x, we just write ln of x. ln of x. Okay, but let's kind of see where these come from. Once again, we can do this on the calculator. Right, we can do this on the calculator. So we have, oh right, mine's backwards, so I want to put the number in first. Most other button calculators, you put ln first. Go ahead and find that ln button. For some calculators, it's sitting above the log button, right? So you have to set second log. You may have to find, it may be right next to it on a TI-89, 84, pardon me. It's below it. So it's on the side there below it. And then E is actually right above it, which is fun. Yeah, hit ln, and we get negative 0.537. So this is negative 0.537, and it's 6. So actually this rounds up to 8, right? 5 and above, give a shove. 4 and below, let it go. No, you don't get to choose whether that goes up to 7 or goes up to 8 or stays at 7. You actually have a rule. There's always a rule in math. Don't expect there to be none. Okay, let's try another one. ln of 192.7. ln. Okay, so 192.7. ln of that is 5.26. Fabulous. That's equal to 5.261. And that makes sense, right? It's a really big number. The other one was a pretty small number, 0.584. That is a fraction, right? It's not a very low fraction. I know that doesn't sound right, but 1/2, not really a low fraction. But it's still negative, and the negative flipped it over, that negative exponent rule, because we're technically asking e to what power is going to be 5.841. A negative makes sense here as an answer. Whereas here, we're asking e to what power is going to be 192? Well, yeah, that's going to be a little bit bigger. E to the 5th is going to be 192. Cool. Moving right along. ln of 10.84, we're asking to what power of e is 10.84? Again, I dare you to do that in your head. While you do that, I'm going to do the calculator. And then I'm going to hit ln. Make sure you don't accidentally hit log. Those are not the same answer. Log base 10 is different from log base e. And so x is equal to 2.383, because the next one's 2. And that makes sense, right? Because 2 squared would be 4. And then 2 to the 3rd would be 8. And this is a little less than 2. So yeah, that makes sense. That makes sense. Okay, cool. Moving right along. ln of negative 3.4. So 3.4, which is negative. Don't forget the negative part. ln. Once again, we get not a number, right? And that again makes sense for the same reason as 10, right? As log, as common log, because for our logarithmic function, it doesn't go into the negative zone, right? It doesn't make sense to have that there. Technically, this is a y if you think about it. Our our x is our answer, and the x doesn't go into the negative part, right? None of this part of the graph is ever used. It's not used, so. Excuse me. I just got some dust in my throat. Okay. So that makes sense. So this is D and E. Common logs, natural logs, very, very similar to each other. Okay, they're very similar to each other. However, there are only 2, right? There are only 2. There's only 2 logs you can plug into your calculator. That's stupid. I don't want to do that. That's not fair. I want to be able to do everything on my calculator. That's not cool. Please don't be the guy that does everything on the calculator. That's just stupid. But it's a valid point, right? Sometimes there's going to be other logs, base 2, base 12, base 147, that you're not going to want to spend 100 years trying to find the answer to. For example, let's read this problem right here. We have a calculator to approximate common logs and natural logs. So, however, some applications involve other logarithms with other bases. For example, the percentage of women who had babies this last year and returned to work is given, is given by f of x is equal to 38.83 plus 4.208 log 2 to the x. So naturally, as the year starts out, right, a lot of people are like, dude, the year's not even over. I'm not going back to work. And then I'm not going back to work. I'm going to stay, or I need to go back to work. There's a lot of time left in the year. And then as the year goes on, they're like, wait a minute, there's not a lot of work left. Why don't I just take this till the holiday? Like, I'm just going to take a couple months, and then I'll start again next year, right? So it kind of tapers off, right? It tapers off. It makes sense. For X years since 1998. So this is one of those ones where X is the number of years past a certain day. We just need to plug it in. if I wanted to find a number of years, that would be difficult because I can't plug log 2 into a function or into a calculator. So far I have log 10 and log e, and neither one of those is log 2. So we're going to use a rule called the change of base rule. So it's going to change your base into whatever you want it to be. Now there's two ways to do this, but basically here's your format. Log a of x is equal to log b of x divided by log b of a. So you're taking both pieces of your original function and you're rewriting it as the division of two of those, where they now are both the argument. Okay, so if you need a numerical example, log 4 of 6 is equal to log 2 of 6 divided by log 2 of 4. And yes, you can choose 2. You can choose it to be x. You can choose it to be 12. And you can also choose it to be choose it to be 10 or choose it to be ln, right? You can choose it to be e. You can make this a log 10. Make it a log e, right? So you can use either one. Those are two ways you're able to plug in the calculator. But let's try this converting thing just a few more times. Just make sure we've got it. So solve the logarithm. I'm going to just go with log 10. I'm going to go with log 10. You don't need to do this either way. We'll solve this last one with log ln. We'll actually do both on the last one. But now we'll do both on the first one. I changed my mind. Let's do both on the first one. So we're going to start change of base rule. I want to change these both to 10. So log 5 of 12 is the same thing as log 10 of 12, or log 12, common log, over log 10 of 5. Okay, so that's the same thing. I put the argument as now not only 12, but also 5. The thing in the parentheses, the thing the log is being taken of. If you're not quite comfortable with common log yet, you can imagine two little 10s down there, right? I put in 10 instead of 5, and I divided the two. But this I can plug in my calculator. So over here, 12 log base 10 would be 1.079 over 5 base 10, 0.699, and then we'll divide the two. Divided by 0.699. I end up with, we'll approximate, 1.544. Oops. 1.544. Fabulous. But what happened if we did that with ln? What if I did that with ln instead of log 10? Well, then I'd have 12 of ln divided by, parentheses, 5 of ln, which would be, again, 1.544. Look at that. Exactly the same thing. So if you didn't catch that on my calculator, what I did instead was ln of 12 over ln of 5. And I got the exact same thing within a few decimal places, right? I mean, if I round the same place, I got the exact same thing. So you can choose log or ln. You should end up getting the same ratio because you're changing both bases, right? All right, another one. Let's do this. I'm just going to use log here. This becomes log of 128 over log of 46. Notice now I'm not saying log 10 of, log 2 of, log 12 of. I'm just saying log of. That's how how informal this whole process is. Log of 12, log of 4. It's just what it is. The 10 gets left off. It gets left off in my speech too. And I end up with, I'm going to round. If you can in your calculator put this in parentheses so you don't have to round, it's better. You can get a little more accurate, but honestly, we're taking it to 4 decimal places anyway, so it shouldn't make a difference. So let's see, 12.8 of log. I'm saying it backwards. It's just how I type. 0.7. It's a 2 up there, not a 5 and above, so I keep it as a 7. I don't get to choose if it's 7 or 8. And then 4.6, and that's 1.526. So now I do 1.107. I'm using my mouse so that you guys can see. 1.526 equals, alright, this is going to equal 0.7254. Oh, no. Just 5. Awesome. Okay, moving right along. If I did that with ln, 12.8 ln divided by 4.6 of ln, I again get 1.6. Whoa, what did I do? Hold on. 12.8 ln divided by, parentheses, 4.6 of ln. Hold on. Okay. 12.8 of log divided by, parentheses, 4.6 of log. Uh-oh. See that, what I did? I made a mistake. I used ln instead of log. Do you see how easy that is? People always say, I even said before, don't be the guy who plugs things wrong in the calculator, but it's always the case. People always click the wrong button. That's why I hate this stupid calculator. Anyway, so this ended up being, let's try that again. 4.6 of log is not 5.1, but 0.662, nope, 3. Okay, so now 1.107 divided by 0.663. That makes much more sense. Okay, now they match at 1.70, and that's what we got from the other one as well. Good thing I double checked, right? It took 30 seconds. A good thing I double checked. This one, we're gonna do log pi e. I love this problem. I love that it has no numbers in it. Well, technically it has 2 numbers in it, but I love that it has no standard Hindu-Arabic numbers. It doesn't matter though, because all of this is represented on our calculator, right? So let's try that out. Let's see, we've got log pi of e. So this is going to convert to log e over log pi. Pretty easy. I'm going to do log first, and we'll do ln. So e log of that, 4.30, pardon me, 0.434 over, we have pi log 0.497971, and then we'll divide the two. So 0.343 divided by 0.497. Okay, cool. So that is 0.873. That wasn't super hard, right? We know pi equals 3.14. We know e is 2.71. So really, it's just it's kind of like example C. Like, it's really not that hard. I know I did those in the wrong order, but let's take a look at what happens when we use ln. ln of e over ln of pi. Well, what's ln of e? Interesting. ln of e is 1. Why would that be the case? Why would that be the case? So if you think e to the ln, excuse me. No, let's do, so ln of e is equal to x, right? And that means natural log. So log of e to the e is equal to x. Fascinating. Make our circle. E to the x is equal to e. What must x be? It's equal to 1, right? So because you're raising the base to its same power, you end up getting 1. Just 1. E is equal to 1, or x is equal to 1. And that makes sense. So then when we take ln of e, it's got to be equal to 1, because we just solved a little mini equation. All right, cool. But we divide that by the pi, ln of pi, and we end up with, around the same thing, and 8.73, in this case 4, but that's just because of a rounding error. Alrighty, so that's change of logs, or change of base, pardon me. Okie dokie, the last thing we are going to do in this chapter is to find some applications of common and natural logs. Not just those, you can really use the applications of any logs, right? We've seen a couple, some inverse ones, but this is really where it comes in, the applications, right? Okay, example number 1. Find the number of women who had a baby and returned to work in 1995 using the previously mentioned equation. Okay, so let's go back up to that equation. We have f of x, Let's write smaller. F of x equals 38.83 plus 4.2. Yep, 4.208 log base 2 of x. Now, how exactly do we plug into this equation, right? It's what did x represent? Where x is for year x since 1980. So 1995 is 15 years from year 80. So we are plugging in f of 15. I will plug that in. None of this changes except the x. So log 2x becomes log 2 of 15. Okay. Gotta start there. When I plug this in my calculator, unfortunately I can't plug in log 2 of x. So if I wanted to plug this whole thing in my calculator, well, 38.83, not too bad. 4.208, not too bad. But let's change this to log 15 divided by log 2. Or ln 15 divided by ln of 2. Ln of 2, it shouldn't matter. Okay, so 15 log of that divided by parentheses 2 log of that equals 3.90 blah 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 times 4.208 following PEMDAS. Now plus the 38.0 nope. Yeah, okay, cool. 83. Alright, so we end up with about 55.27. Awesome, 55.27, right? 55.27 women returned. You got 0.27 of a woman. That's creepy. I don't know what happened there. So we're going to round and we're going to say 55 women. 55 women returned to work, so that way it'll fit our model in 1995. Okay, cool. Alright, that was pretty easy. Let's do the next one. Wetlands are classified as bogs, ferns, marshes, and swamps based on a pH level value. A pH between 0.6 and 7.5, such as that of Summerby Swamp in Michigan's Hathawan National Forest, indicate that the wetland is a rich fen, where a pH between 4 and 6 in the wetland is a poor fen. And if the pH falls below 4, it is called a bog. A. Suppose the hydrogen ion concentrate, H3O+, of a sample of water from the wetlands is 3.6 times 10 to the negative third. How would you classify this wetland if the pH is calculated with the function pH is equal to negative log of H3O+? Interesting. So there's a lot of stuff we got to plug in. First off, we got to plug in the concentration, right? So the pH is equal to negative log. Now this log has no subscript, so we know it's a common log. We know this is log base 10 of, let's see, what was H? 6.3 times 10 to the negative third. 6.3 times 10 to the negative third. Alright, that doesn't really help me in scientific notation, so I think I'm going to break it up. I'm going to use my rules of logs. Rather than plugging in a number or converting that, I'm just going to use my rules of logs. It's going to be easier for me. So minus log of 6.3 plus, because that's what this is, right? 6.3 times 10 to the negative third. So I'll just go like this. A log of 10 to the negative third. Awesome. That is equal to negative log 6.3. Distribute that minus. And that minus, and we'll just keep it. Negative 3 log 10, right? That power comes down. Now I've got this. Distribute that minus, we get negative log 6.3 minus 3 log 10. Well, wait. Log 10 of 10, let's just double check ourselves here. Yes, if you have the same, it's 1, right? So, minus log of 3.6 minus 3, because this whole thing is 1. So check that out. Using my rules, I made my life a little easier, right? I made it a little easier. So now, let's just find log 6.3. 6.3 log. Take the negative of that and subtract 3 from it, and you get, oh wait, that didn't work. Hold on. So 6.3 log, wait, what happened to my negative? So we got that, my apologies when I put that in, that should have been a plus 3, right? Should have been plus 3 because I have negative. Okay, so now we clear this, we need the 6.3 as a log, that's really a long number, make it negative, and add 3 to it, and we get that this pH is 2.2. That's equal to 2.2, which would be classified as something under 4, so we would say this is a bog. This is definitely a bog, right? 2.2 is way too low. Alright, B, what if the pH was 6.5? If the pH was 6.5, what would the concentration be? I think that's their question. What would the concentration be? I'm going to use this space over here and a different color to show that we are in a different problem. So, we have 6.5 on this side is equal to negative log of this, this element. But for our clarity's sake, we're just going to call it x. Okay, so log x. Alrighty. Well, let's convert this. Let's convert it. Let's throw in our 10, and let's make our circle. So we have 10 to the 6, oh, and my apologies. We have to get rid of the negative first, right, because it's negative 1. So let's multiply both sides by negative 1. Negative 6.5 equals log base x, right? Now we'll make our circle. So we have 10 in there, we'll make our circle. 10 to the negative 6.5 equals x. What would the concentration be? So 10 to the, whoops, 10 exponent 6.5, that is negative. Notice I love button calculators. 0.000000316. Okay. X equals 0.000000316. Why do we make that a little easier? That's 1, 2, 3, 4, 5, 6, 7 places. 3.16 times 10 to the negative 7th in scientific notation. That's pretty unsaturated with this element. That would have to be an extremely low occurring element for this to be considered a what? What is a 6.5? 6.5 is over 6.5 is higher than a rich fen. So it would be way, way high. Okay. Alright, last but not least, let's talk about independent languages. The number of years NR since two independently evolving languages split off from an ancestral language is approximated by NR equals negative 5,000 LNR. Okay, so one with a natural log this time. Where R is the percentage of words in decimal form from the ancestral language common to both languages now. Find the number of years to the nearest 100 years since the split of each percent of common words. Okay, so notice it says in decimal format. But all three of these that they want us to find, 85%, 35%, and 10%, are written as percents. So let's just start by converting this to a decimal. 0.85. Put it over here. 0.85 instead of percent, right? Because that's how this function works. Now we're going to plug it in. 0.85 is equal to negative 5,000 ln of 0.85. So what would that be? Negative 5,000 times 0.85 negative 0.163 times 5,000, that is negative. There will be 812.6. They said to the nearest 100 years. So that's going to be about 800 years. The number of years, well, they'll have 85% in common. We have to go 800 years back. Okay, that's fine. Now 35%, 0.35, right? We move it 2 decimal places. It is not 3.5. You have to be very careful. So move it 2 decimal places. Now we'll plug in 0.35. See if you can get this one on your own. Pause the video if you need to. And then 0.35 here. Okay, we get negative 5,000 times 0.35 ln. That is a point, it's a decimal spot, so it makes sense that this exponent is negative. Nope. 5 times. Nope. 5,000 negative. That doesn't make sense. Hold on. 0.35 ln times 5,000. My apologies. Okay. 5249.11. So in order to have 35% in common, we have to go back 5,000 years, right? 5,000 years. Okay. And then last but not least, we have 10%, so we have 0.10, right? Plug that in. And we end up with negative 5,000 ln 0.10 or 0.1, same thing. 5,000, oops. So 0.1, that'd be negative 2.3, okay, times 5,000, negative 5,000. That would equal 11,512.93, or rounded correctly, 11,500 years. Now we should tack years onto each of these. Whoops, this would be 5,300. 53 years. Okay. So it has been 800 years since the split of 85%. So 85% are different now. 5,300 years since only 35% are different, and 11,500 years since only 10% were different. Interesting. Oh, sorry, since only 10% were only 10% were different. Yeah. All right. So those are 3 examples of where it can be used in real life. We've talked a lot about logs and common logs and natural logs in this section. That closes out the chapter on everything logarithms and inverses. Hope you like it. Let me know if you have any questions. See you later.